I'm not sure how I'm going to introduce Pavel. Pavel is and we are not going to be very formal, but for those of you that don't know him, he's a professor in the Charles University in Prague, in the Czech Republic, and he has been very active in the field of quantum phase transitions, ground state quantum phase transitions, where they have some very nice papers, and in fact some reviews. I don't know how he is able to write so much. But also he was one of the fathers, let's say, of the excited state quantum phase transition concept, and the seminal papers on this subject can be traced back to him. So several of them, and especially this year, I think it's a very good. Well, in any case, he will be an excellent option as a keynote speaker for excited state quantum phase transitions, but especially this year where he has published this very nice review paper on excited state quantum phase transitions. So now he's the right person to give this overall view on the field. Yeah, there is some radio or something there. Yeah.
Hello.
So, okay, the chat is working. I was checking. Okay. Now we are 4 minutes in advance. So let's 27. By the way, the talks are being recorded, and well, we will remove the first half an hour. I don't think that this unless somebody wants to keep the picture of Pavel with his beard, and his father. But we will, after some editing, we will post the videos in the web page of the. In the web page of the meeting, of the ESQPT 2021 meeting. So in case you miss any of the talks, they will be there. There are still some people joining us. 31.
Good afternoon, good morning, and good night.
Hello. Hello, Jorge.
Hi.
Hi.
Hello, Jorge.
Hi. Armando, Pavel, Jorge.
Hola. ¿Qué tal?
Curro.
Hola, Jorge.
Hola, Jorge, ¿cómo estás?
¿Qué tal? ¿Qué tal todo?
¿Todo bien?
Todo bien. ¿Cómo te va?
Qué bueno, qué bueno.
Bien, no te cuento.
Bueno, acá me parece que hasta Pavel chapurrea el español.
Okay. Stransky seguro, Pavel Cejnar quizá también.
Pavel will translate. I will speak Czech and Pavel will translate to Spanish. So shall I start sharing already the screen?
Yeah, you can share your screen.
So hopefully it works again. So is it okay? Do you see everything?
Yeah.
Even the mouse, the hand?
Yes,
okay.
And the mouse with the virtual hand.
Okay. So tell me when I shall start.
Okay, It's 15:59. So I will not repeat the presentation of Pavel. I have already presented it. For those of you that have arrived late, probably you know him, and some of the ones that have arrived late know him much better than I. So I think that you can start. It's 15:59. So you can just do your warm up your voice.
¿Cambiaron algo?
So, hello everybody. I wanted to thank very much Kuro and Jose and Rick for this excellent idea of having this series of seminars on the ESQPT subject. It is indeed a nice way how to somehow make these difficult times better and easier for all of us. So I'm very honored to give this introductory talk. So I selected a title which somehow refers to the famous book by Kesey and the movie also by Miloš Forman. And my intention was somehow to emphasize that this is going to be an introductory talk. That means a flight over the topic. I will try to present some perspective on the topic. So that's a flight over the ESQPT topic. And also the second reason is the second reason is that we are already 1 year in this strange situation. So I already feel like a patient of a mental clinic somehow, and I take this occasion as a kind of collective therapy. So let's have this collective therapy, this series of meetings. So the program of my talk is the following. First of all, I will very briefly introduce what the ESQPT is for those who are not familiar with that concept. Then I will go through some systems in which you can observe these effects. And then I will present a bit of theory on this subject. I will show some consequences, and finally I will discuss some analogues. That means some systems which are not exactly the systems of the type where you expect an ESQPT, but you finally observe an analog of ESQPT in such systems. And okay, this program is roughly taken from our recent review that Kuro mentioned. Actually, it is still in the archive, but it is already like accepted in the Journal of Physics A, and it's in press now. You can find the PDF already there, but you can also find it as a preprint. So please feel free to interrupt me and also to tell me if there is some problem with the presentation or anything. So the first point, what is the ESQPT? So the ESQPT is the excited state quantum phase transition, and it is a singularity in the energy eigenspectrum of an infinite system. So here is a picture of the first example of an ESQPT that is taken from the interacting Boson model of nuclear physics. And it's somehow the spectrum along the transition between O6 and U5 dynamical symmetries. So here you see the spectrum, the full spectrum of all zero spin states, and you observe that something is happening in this spectrum. There is some effect, some strange effect at some energy somewhere here. And because this model in this regime is integrable, you can identify some additional integrals of motion on top of the energy and angular momentum. And if you somehow like disentangle the two spectrum into the components of different values of this additional conserved quantum number, you find out finally the spectrum which is singular, which is responsible for this singularity, and it is shown here. Okay, so it's for another number of bosons, but anyway, I mean, this is the singular spectrum where you clearly see the effect of an increased level density, this very well-known now picture known from many other systems, actually, not only this interacting boson model. It immediately turned out that this singularity is also connected with the singularity of eigenstates. Here you see the wave functions of two selected eigenstates from that spectrum, and you see that when the level crosses the ESQPT region, there is a singularity in the wave function. I mean, here you see the wave function or squared wave function as a function of this control parameter eta in this case. So there is some singularity here. The same happens also for the other states, but sooner, because it crosses this transition sooner. So I would say that ESQPT is a singularity in the energy eigenspectrum, and it also affects the corresponding eigenvectors. Now, in which systems this effect can happen, can be observed? So I would say in general, this happens in many body systems with potentially infinite number of constituents. That means this number of constituents n, typically a number of particles, number of bosons or something like that, is a size parameter. But so this size parameter can go to infinity, but at the same time you need that somehow the number of degrees of freedom remains constant. It does not increase with the size parameter, and you prefer it if this number of degrees of freedom is low. So those degrees of freedom must be some collective degrees of freedom of that system, and they typically appear in systems with some long-range interactions. So here I give some examples of systems in which you can observe the ESQPT. So this is the fully connected Lipkin model, for example, which is in fact a fully connected spin or qubit system. That means fully connected means that the interaction is of infinite range. All qubits interact with all the others. So you can introduce this quasi-spin algebra composed of Pauli matrices associated with individual spins. And in terms of that collective algebra, SU2 algebra, you can write down the Hamiltonian, like here, this Hamiltonian. And this Hamiltonian actually written here shows like two different types of ESQPT or of ground state QPT, I would say. The first is this second order QPT, and the second is the first order QPT. And then there are some associated ESQPT structures which you see here. It's again that ESQPT of the similar type as we saw in the previous pictures, which somehow continues the ground state QPT of the second order, or you can have some different structures in the level density, basically, which accompany the first order ground state QPT. So in these systems, you really can see very clear examples of ESQPTs. Okay, I already mentioned here that the SU2 algebra can be cast also in terms of some bosons. So this constitutes a completely different set of many-body models in which you can also observe ESQPTs. These are the interacting boson systems, which are used in nuclei, in molecules. So the Lipkin model is the simplest example, where you have like S and T boson, like two scalar bosons, but you can have many other or several other types of these systems, which is for example, the molecular vibron models, in which you have the additional boson up to the S boson is not the T boson, the scalar T boson, but it is either the tau or P boson, which has 2 or 3 components. So these are the molecular vibron models which have 2 or 3 complete number of degrees of freedom. Or you can also have this nuclear interacting boson model, which has in fact 5 degrees of freedom. In all these cases, you can somehow reduce the number of degrees of freedom because these models have some conservation laws, and if you select appropriate subsets of states, you reduce the number of degrees of freedom to 1 in these Lipkin or Vibron models, or to 2 in these interacting boson models. So the Hamiltonian is always of this type. You have the one body plus two body one body terms and two body interactions. So let me give an example from this molecular Vibron model. It's a very nice example, actually, from the work of Kuro and collaborators. This is basically the spectrum of the two-dimensional Vibron model. Or, I mean, this one with the tau bosons arranged into the grid, where you have energy on the horizon or on the vertical axis and the angular momentum on the horizontal axis. And you see that the points are arranged in such a way that there is a defect of this grid here, and that defect can be associated with quantum monodromy, but also equivalently with an ESQPT. And actually, this arrangement is similar to, as I mentioned, to that disintegration of the total spectrum into the subspectra with different values of the integrals of motion. So if for each L you would have a different spectrum, but the spectrum which actually shows the ESQPT is the one with L equals to 0. And now the big advantage of this example is that it is an experimental example also, because these triangles are actually experimental points. So you can really observe that this is a perfectly measured quantity. This defect of the spectrum, which is equivalent to the ESQPT, is actually an experimentally confirmed phenomenon. So here I have another example from the interacting boson model. Now I'm not already in that integrable region of the U5 to O6 transition. So now I cannot reduce the number of degrees of freedom of the model to 1, but I have 2 degrees of freedom, and it turns out that in this case the singularity is not anymore in the level density itself, as in the previous cases. We saw that always we observed that the divergence of the level density or some other effects directly in the level density in the previous examples. But now we see similar effects, but in the first derivative of the level density. So here you see a color plot of the first derivative. So somehow the blue color means positive value, red means negative value of this derivative, and you see also these cuts of this plane here, so you can imagine what happens there. So there are some breaks or divergences or such effects in the level density, in the first derivative of the level density, actually, that you observe for some Hamiltonian of this interacting boson model along the first order QPT transition from spherical to deformed nuclei, actually. So this is an example already, like a less trivial example of an ESQPT. Actually, you see that you have plenty of ESQPTs already in this system. There are many singularities in the level density already visible. Now, speaking about interacting boson systems, I would like to highlight these systems which are like boson systems, which are applicable in the physics of Bose-Einstein condensation. Actually, these are very interesting models which show neat examples of ESQPTs, actually. And the big advantage of this is that you can play with such systems in the laboratory. And a disadvantage of the molecule is that you simply prepare it at a certain value. I mean, the molecule exists somehow, and it already has a fixed value of the control parameters, so you cannot play with that. But with these Bose-Einstein condensates, you can change the parameters. You can simulate such systems in the laboratory. So you can also play with some dynamical consequences of ESQPTs, etc. So again, the Hamiltonian is of the same form. Now maybe the one-body term. I don't show it in the diagonalized form because it can involve hopping terms between the sides. And again, you have two-body interactions, which are usually inter-side interactions, or you can have interactions of bosons everywhere. But anyway, I mentioned two types of such models. The first is two-side Bose-Hubbard model, where you typically have like two types of bosons, B plus, B minus. So you have two sides, plus and minus, and bosons on those sides. And this such Hamiltonians can simulate or model the Josephson junction, actually, and the conductor-insulator phase transition. And these systems, of course, because these are simple bosonic systems, they exhibit very neat examples of ESQPTs. Recently, there is also a preprint now by Paulina Feldman and collaborators showing that ESQPTs can be also observed in three-mode boson model, which is a model for a spinor condensate that describes spin degrees of freedom of Bose-Einstein condensates formed by spin-1 atoms. So in this case, you have like a three-mode bosonic model. And because of some conservation laws, again, I don't want to go into detail, you can, in a certain subset of states, you can again observe this type of ESQPT which affects directly the level density, which is somehow implicitly related to systems with a single degree of freedom. So these systems are now proposed as an experimental platform, in fact, for testing various features of excited state quantum phase transitions. Well, another system which is potentially experimental is this coupled atom field system, basically the decay model, which simulates like two-level atoms interacting with single-mode photons. So cavity quantum electrodynamics, but you can also somehow reformulate the same Hamiltonian to get different physical contents. In other words, you can emulate it also in different ways. And this Hamiltonian again uses, okay, this Hamiltonian actually has 2 degrees of freedom because the atomic subsystem has 1 degree of freedom, that is the quasi-spin system. The photon subsystem has also 1 degree of freedom, so altogether you have 2 degrees of freedom, and you indeed observe neat examples of ESQPTs in the spectra, in the level density itself. But then you can also reduce this model to 1 degree of freedom by considering, for example, the regime in which you set this parameter delta in the Hamiltonian equal to 0. In that case, you obtain what is usually called Tavis-Cummings regime of the model, which has an additional conservation law. That conservation law is basically the number of bosons, that means number of photons, plus the number of excited atoms. That number is conserved, and because of that, you can reduce the number of degrees of freedom to 1, and you can observe ESQPTs directly in the level density, or you can go to the Rabi regime, where you make use of this adiabatic separation of the 2 degrees of freedom, and basically you observe effects in only 1 of the degrees of freedom, usually in the field degree of freedom. And again, you observe similar ESQPTs, not in the first derivative of the level density, but directly in the level density. Finally, there are many other systems where you can see such effects. They can be even fermionic systems. For example, the Lipkin model, of course, can be formulated in the fermionic language, or you can see it in a very similar way. You can formulate a fermionic pairing model. You can somehow extend it. You can play with this. You can have Bose-Fermi systems also, like this one in the third line, because here you form the, actually all these operators are generators of the SU2 algebra. All these 3 lines are generators of the SU2 algebra. So it can be done in the fermionic way or in the Bose-Fermi way, like here. So this is called a bilayer model, which somehow is also used in the condensed matter context. Finally, you can also define systems which do not even conserve the particle number. So they, instead of a particle number, they conserve something like this. So these systems are typically used in like models of some atom molecule condensates. That means you have systems where atoms can be like atoms which are composed of two like molecules which are composed of two atoms can disintegrate and be formed again. So you have a system which allows such disintegration, etc. So, and in this system, for example, can be, for example, formulated in terms of a deformed SU2 algebra. So usually when you can identify some algebra, even in this generalized sense, you can somehow define the relevant degrees of freedom, which are collective degrees of freedom, and you can usually, in most cases, find some critical effects even in the spectra of excited states. Okay, so this is like very briefly about those systems. The last point I wanted to mention here, that is of course a challenge. Can we find ESQPTs also in true many-body systems, like in the systems in which the dynamics is not purely collective? That means in systems in which the number of constituents going to infinity implies the number of degrees of freedom going to infinity as well, because every constituent brings a degree of freedom or some degrees of freedom. So you expect that the number of degrees of freedom are proportional to the number of constituents. So if the system is not collective. So do we have examples of ESQPTs like criticality in excited spectra also in such systems? Okay, there are some, it's not, I mean, there are examples of such singularities in the excited spectra, but so far it was not really treated in the language of the ESQPT. So these singularities are called many-body localization phase transitions or eigenstate phase transitions. Here you see actually an example from the Heisenberg chain in a random magnetic field. So somehow so there is some parameter of the model, there is an energy of the model, and somehow the spectrum shows clearly the two phases in this picture. One of those phases is a delocalized phase, which, okay, I will not somehow go into details in these examples. And the other phase is many-body localized phase. Those phases actually differ by the localization properties of these wave functions. And it seems that in the excited spectrum, there is like a more or less a sharp border between those two types of the eigenstates. But okay, as I said, this is just like an excursion to another field because this is not yet somehow integrated into the language of ESQPT. But I think it is also something which can be later done. Okay, a bit of theory. I would say like the most important thing is that in the present form, as if we're speaking about these systems with a finite number of degrees of freedom, the ESQPTs are always rooted in the classical dynamics somehow. So these are effects which come from the classical dynamics of the system, and they appear in the quantum spectra. So why can we say this? It is because for the systems with finite numbers of degrees of freedom, it turns out that the scaled infinite size limit is equivalent to the classical limit. Okay, so basically in the classical limit, you deal with the classical phase space, which has some finite dimension 2f, where f is the number of degrees of freedom, and you have a classical Hamiltonian. And then the most common source of a singularity of the ESQPT singularity in the quantum spectrum is the stationary point, a stationary point of the classical Hamiltonian. So the most common type of the stationary point is the non-degenerate stationary point. That means a stationary point which is locally quadratic. And such a stationary point can be characterized by a number called index, which goes from 0 to the dimension of the space. And basically that index determines the type of the stationary point, whether it's a local minimum or local maximum, or in majority of cases, of course, a saddle point, some type of saddle point with some number of positive and negative eigenvalues of the Hessian matrix. Actually, this index is the number of negative eigenvalues of the Hessian matrix. Now, once you know the number of degrees of freedom, which is the dimension, basically two times f is the dimension of the phase space, and once you know the index of the stationary point, you can determine what will happen in the level density, because as shown on this diagram, you see that the ESQPT caused by such a non-degenerate stationary point always affects the f minus first derivative of the level density, and according to the index, according to the type of the stationary point, you can see these four effects, like either a step up or down, or divergence, either upward or downward divergence of the level density, or that f minus first derivative of the level density. Okay, so not all stationary points are non-degenerate. Some of them are degenerate, but they are rare, I would say. They mostly appear in some non-integrable systems. And in that case, the singularity can be even stronger than in the f minus first derivative. It can go to a lower derivative, but it cannot be classified in this way as I showed now. So you have to consider each case separately. Here I have an example, for example, of a separable minimum, and okay, I will not maybe discuss this. It can be shown that if the minimum is higher than quadratic, that means it's flatter than quadratic, then the singularity in the level density appears in the lower derivative of the level density than the f minus first derivative. Not all ESQPTs actually are due to these stationary points, because especially in these many-body systems which have a finite Hilbert space, somehow the volume of the phase space must also be finite. So there exists a boundary of the phase space, and there can be some maxima, minima, or saddles on that boundary, and these can also cause some stationary, some ESQPTs, or some singularities in the level density, which are, however, not associated with stationary points of the classical dynamics. Here you see an example from the interacting boson model, where you actually see a singularity in the spectrum which is not associated with any true stationary points of the classical Hamiltonian. It is a boundary effect, because of course the IBM is a compact model with a finite spectrum, so it's the phase space is bounded. Now, I also want to mention some frequently asked questions, so to say. Maybe they are not asked so frequently, but I call it like that. So the first question is, which, I mean, it is something that people very often do, that you simplify the problem of searching for the stationary points by reducing the dimension. You simply set all the momenta in the Hamiltonian to 0, and you look just in the configuration space for the stationary points. Can we do this? The answer is no. I mean, it is a very often used method, and it usually gives good results, but not always, because you can find also stationary points which have non-zero values of momenta. That only means that you may ask, okay, how can I have a stationary point with a non-zero momentum? It only means that that momentum is, I mean, this is a canonical momentum, of course, and that canonical momentum is not identical with the mechanical momentum. So at the stationary points, always the mechanical momentum must be 0, but it does not imply that the canonical momentum is 0. So it sometimes happens. It's not it's relatively rare, but again, you can find examples, for example, in this interacting boson model, where there is a, you see here that there is a, like these are actually the coordinates and momenta associated with the stationary points responsible for these ESQPTs, and some of them have non-zero momenta. So the method when you set momentum to 0 would not disclose these stationary points, so you would miss some ESQPTs actually. The second question: can we speak about an order of the ESQPT, like first order, second order? This is also often repeated, that people call ESQPTs by an order or classify them by an order. Again, the answer is no. There is no order of an ESQPT. First of all, even if the system is integrable, like here, you see that all the levels which pass through the given ESQPT, they show the same effect. That means some singularity in their energy dependence, but that singularity cannot be classified by an order, because some derivatives of the energy with respect to the control parameter are diverging, for example. So we can, in this case, we can say that there is like a diverging derivative, and that means there is no order of that transition. But it's not the main thing. The main thing is that in non-integrable systems, like this is an example of a spectrum that you see here, not all levels have the same type of singularity. And it can even happen that some levels have no singularity at all. They may even pass through the ESQPT. But okay, in general, you see here that there are various effects, like various levels show different effects when they cross the ESQPT. So in this case, you cannot say that it is the first or second or third order. Simply, the only thing you have at hand is the singularity in the level density. Again, the plot that is shown on the right-hand side. It either appears in the level density or in the first derivative of the level density or in some higher derivative. But this is the only classification that you can give. Third, do we always have some order parameters which characterize these phase transitions, these ESQPTs? Again, the answer is negative, because although I have to say that in many cases we can find such order parameters. And okay, the reason is that the order parameter, this concept, is related to the phenomenon of spontaneous symmetry breaking, actually. So once you have a spontaneous symmetry breaking, you can define an order parameter which is associated with the given phase transition. But in the ESQPT case, very often we do not have any symmetry spontaneously broken. And in those cases, we can hardly find an order parameter, actually. So here again, I see two very similar examples. In one case, that's the Rabbi model, that means the one regime of this decay model. You observe that there are those the levels which are above are single levels, but the levels which are below this ESQPT are parity doublets. You observe that convergence of the levels at the ESQPT border. Actually, so here you have parity doublets. So apparently there is a spontaneous symmetry breaking connected with this QPT, and it is somehow reflected by the corresponding ESQPT. And in this case, you can perfectly define the order parameter, which is Jx in this case. But here you have another example from basically the same model, that is the Tavis-Cummings regime of the decay model in the subspace when this number of excited atoms plus the number of photons is equal to the number of to the total number of photons. That subspace is critical. It shows the ground state QPT and also the ESQPT, but there are no parity doublets here. So there is no spontaneous symmetry breaking mechanism responsible for this transition, and you would hardly find an order parameter in this case. Another question: does the classical limit provide all information on the ESQPTs? Because people are very often asking, okay, it seems that it is completely classical effect. The ESQPT looks like completely classical effect. So is there anything quantum on it? So I would say it's not entirely classical. Of course, the finite size scaling, like scaling with the size parameter as well as scaling with the control parameter or with energy. These are very important things which accompany these ESQPTs, but they are not studied in many systems. Actually, in some systems, people found some scaling exponents already, but I mean, this is rather like, I would say, exceptional. Not all the systems were studied like that. So it is certainly very useful to study the finite size scaling effects. And this is purely quantum. This cannot be determined from the classical limit. The classical limit gives us only the classification of the ESQPT. So we know what we will see in the asymptotic level density, but the way how we approach to this infinite size limit, it is a completely quantum thing, and we have to study in this question in purely quantum models. So the last question is, I mean, do the ESQPT split the parameter energy plane into some quantum phases? So this is the famous question. There are phase transitions, but are there any phases? So what are the phases? So I would say the answer to this question would be finally a careful yes. I think that there exist some quantum phases which are like divided by the, or which are separated by the ESQPT borderlines, but it is sometimes difficult to define these phases. I will show here an example, again taken from the decay model, which we already saw. So this is the level density diagram. So we see these singularities in the first derivative of the level density. And now here on the right-hand side, we see a spectrum taken along this line in the parameter space. So here we observe some, I mean, these D, T, C, N, and S are some quantum phases of the system. They are separated by the ESQPTs, by the ESQPT critical energies. And you can see those phases in this lattice. So what is this? This is a so-called Perez lattice, which is nothing but the spectrum of the system, which, I mean, the energy is drawn along the horizontal axis. So this is basically the energy. But instead of showing the spectrum only as points or only as lines along this horizontal axis, you also show on the vertical axis an expectation value of some quantity, which in this case is the atom field interaction Hamiltonian. So you show the atom field interaction Hamiltonian expectation value on the vertical axis. And you see that somehow the lattice in this plane shows some features. Actually, you see that in some places of the lattice there is a regular arrangement of points, and those are actually regular, I would say, regular states which do not show quantum chaos. But on some other places you see chaotic arrangements, and those are states which actually show quantum chaos. But for us now, more important thing is that the lattice somehow changes its qualitative features when you cross these borders. For example, when you cross this first borderline between the phase D and TC, you observe that there are some branches of points which appear in the lattice, which were not before, and they are above this ESQPT borderline. So it is sort of some dynamical phase within these lines. The lattice remains more or less the same or qualitatively similar, and then again there is some qualitative change. For example, here it is the slope of this upper line, which somehow changes the character of the lattice, and so on. So I would say carefully that, okay, there are some dynamical phases observable in this lattice, so we can somehow define quantum phases, although we probably do not have some order parameters for characterizing these phases, or at least not trivial order parameters. Now, you can. This is also a nice thing, that if you somehow locally average these values, these expectation values, if you simply take several points in a vicinity of the given energy, and then you make an average of those points, you get this line, which is this red line, which is seen here, and that line shows exactly the same singularities as the level density. That is an interesting, that it can be proven. I mean, we know why. It is more or less trivial. I'm not going to show it, but this clearly demonstrates that the lattice, that the structure of eigenvalues, of eigenstates, is actually changed somehow, so that if you averaged locally in energy, you observe this non-analytic behavior, which precisely corresponds to the non-analyticities shown in the level density. Okay, some consequences. So I see that it takes me probably more time than I wanted, but okay, maybe I have to like to go faster. So I want to show some consequences briefly. So you can find thermodynamical consequences, you can find dynamical consequences, and I want to mention especially two types of dynamical consequences. That means consequences in quantum quench dynamics and in slowly driven dynamics. So first, the thermodynamics, but very, very briefly. So we all know from the textbooks that there are two types of thermodynamics, the canonical and microcanonical. And we also know that they are supposed to converge in the infinite size limit, in the thermodynamic limit of the system. And you see that the microcanonical thermodynamics, which actually differs from the canonical one by the fact that the thermalization is not done by some thermal bath, which is external in the canonical concept, but in the microcanonical description, the thermalization takes place via some internal mechanism. So the energy is conserved. So energy of the system is fixed. So it's better for finite systems actually to use this microcanonical description. And there actually everything derives from the Boltzmann definition of the entropy, which is basically the logarithm of the level density. And we know that the level density is affected by ESQPTs. It has a singularity. So the singularity must, of course, appear in the thermodynamic description. So that would be the conclusion. But, okay, there is one big but, because in these finite F systems, that means systems with finite number of degrees of freedom, it turns out that the canonical and microcanonical descriptions do not converge in the infinite size limit. They actually converge if you increase the number of particles as well as number of degrees of freedom. But in our case, we keep the number of degrees of freedom finite, and we only increase the size, the number of particles. And in that case, the two pictures do not converge, and the ESQPTs singularities actually appear only in the microcanonical thermodynamics, but not in the canonical one, usually. So here is an example. Again, I don't maybe want to really discuss in detail this example. So I skip it because I'm running out of time. Now, the dynamical consequences. I mentioned those consequences in quantum quench dynamics. We recently had a paper which is on a preprint now. Okay, it's already accepted, but it is available as a preprint, which gives some understanding on what's happening in these quantum quench dynamics influenced by the ESQPT. Anyway, I mean, there are many other papers also dealing with this question, but I just wanted to say that my pictures will be from our recent paper. So what is the quantum quench? This is a method of a non-thermal excitation of the system. You prepare a system with the Hamiltonian at a certain value of the parameter, and then you change, like you suddenly change the parameter to another value. So the initial state, which is an eigenstate, usually the ground state of the initial Hamiltonian, has a certain distribution in the eigenspectrum of the final Hamiltonian, and it evolves somehow. And now the question is, what happens if this distribution in the final Hamiltonian is located in the ESQPT region? And the answer is that in those cases, usually you see effects in the quantum quench dynamics. That means in what happens after this quench, the dynamics after the quench. So here we see an example of the survival probability. So in this case, it is again the Stavis-Cummings model with this subspace with, as I mentioned, with that critical subspace where you see the ESQPT I showed before. But this is a non-critical quench. In this case, we produce the final system. I mean, the initials, once again, the initial state expanded in the final Hamiltonian eigenbasis does not overlap with the ESQPT. So in this case, we have a non-critical behavior. I mean, it's like a typical pattern of some revivals of the initial state, which you can perfectly visualize by the evolution of the Wigner function in the phase space. I mean, you know this Wigner phase space distribution somehow emulates quantum properties of the system. It is like something which can be used instead of the wave function. So it's some distribution in the phase space, and the initial state can be represented as this Wigner distribution. And then what happens when you do this quench is that, of course, this initial distribution is somehow evolves by the final Hamiltonian, and that evolution is basically this rotation, like classical rotation along the classical trajectories. So what happens is that this is the initial state, and then you have snapshots of the evolved state at various times, and it's clear that as this Wigner distribution goes around these trajectories, then it overlaps repeatedly with the initial state. So these are those revivals of the initial state, which are seen in these plots. Here you see the survival probability in the log-log scale, and here it is linear scale. So you see this weakening 1/t, actually weakening revivals, which appear again and again in the spectrum. And it's nothing but this circulating of the Wigner distribution. But now what can happen is that there is a stationary point, and that is actually when this exactly happens when the distribution, actually when the distribution of the initial state in the final eigenbasis, if it has an overlap with the ESQPT energy, then there is a stationary point usually located somewhere in this energy landscape, in this classical energy landscape. And what happens is that actually this Wigner distribution is captured at that point. That's clear because it's a stationary point. It's not totally captured because there is a certain spread of that distribution, but it's partially spread. It's partially captured. And it leads to this strong suppression of the revivals. As you see here, there is practically nothing. So this is exactly what is observed, what was observed already like long time ago in some numerical studies of this quench dynamics. Or you can even, I mean, there is even another situation when you somehow produce the initial state right at the stationary point. Okay, so it can also happen in some cases. It can be also realized, for example, in this Stavis-Cummings model. And what you observe in those cases is that you basically suppress the very decay of the initial state. So the initial state does not disappear. It is always partly there. Somehow the state does not fully leave the initial position because there is a stationary point connected with that initial position. So this is roughly and very vaguely something about those effects. I think there will be, maybe later we will probably have talks about this, like more detailed talks. Now, this is experimentally important because you can actually do this quantum quench dynamics experimentally. What you actually what you usually observe is not this survival probability, but you usually observe some expectation values, evolving expectation values of some observables. Like here we observe, for example, number of photons in the cavity in this decay model, and you, in some cases, observe really effects of the similar type I just explained. That means just this suppression of the revivals in this response, suppression of the oscillations in this region when the quench is critical. In some other cases, there is practically no effect, and this is connected with the fact that once you have a system which is partly chaotic, those or fully chaotic, which can happen in some domains of this parameter space of this decay model. In those cases, you really do not see effects of those stationary points because the dynamics is already chaotic, and those effects I described on the previous slides, they are actually connected to integrable systems, and if the system is not non-integrable, the effect of the ESQPT is somehow blurred. You don't see much, in these responses here. Actually, you can see the chaoticity already. Here, the plots on the right-hand side are actually the distributions of the initial state in the final eigenbasis. So you see here in this decay case, in this more chaotic case, that part of that distribution is already chaotic. So this is what I wanted to say. Okay, I wanted to make also the advertisement for the talk in the next week, because there is a more sophisticated method which can be somehow cast in a similar way as this quantum quench dynamics. This is connected with these out-of-time ordered correlators, and these are especially good indicators of chaotic dynamics, and they can also be indicators of ESQPTs. The difference from this quantum quench is that in quantum quench dynamics, I considered expectation values of some time-independent quantities, whereas in the autox, you always deal with, you can somehow formulate this problem as a problem of an expectation value of a time-dependent quantity, for example, a quantity which looks like this written here. But okay, I will not say more because this will be a topic of the forthcoming talk. Well, there is also, of course, an effect in driven dynamics. Again, this is experimentally very important question. So now the setup is different. Before we changed the parameter abruptly. Now imagine that you have a Hamiltonian H0 and plus lambda H prime, and this lambda is very slowly changed from some initial value to some final value. Okay, and so this is a very important protocol because basically it's called quantum state preparation protocol. It is a basis for adiabatic quantum computation, for example. So this is experimentally important. Now, the method, there is an adiabatic theorem of quantum mechanics which guarantees that if you perform this change of this parameter sufficiently slowly, you do not your Hamiltonian remains in the intermediate eigenstate. That means if you start, for example, with the ground state of the initial Hamiltonian, the system remains in the intermediate ground state all the time up to the final point. So in this way, you prepare the ground state of the final Hamiltonian. But unfortunately, the life is not so easy when you have a QPT, for example, because in the case of a QPT, you see here that the adiabatic theorem is not valid, or is not easy to satisfy, I would say. Of course, it's valid always, but you would have to slow down to such slow values that it would be practically unfeasible to realize such protocols. So especially in the case of QPTs, you really need to carefully study such adiabatic protocols, or slowly driven dynamics, because you always populate the excited states. And the ESQPTs, which are connected with these Hamiltonians, are somehow contributing to this problem. They influence also the ground state populations. So these are important in the evaluation of the efficiency of these quantum state preparation protocols. So here you see some examples from the Lipkin model, where you actually see this is the first order ground state QPT, and now you drive the system very, very slowly through this first order. I mean, the size of the system is very small, like you have like 4 qubits actually, which is nothing. But you see that even for this low number of qubits and low speed of driving, you populate the excited state. So if you go the first excited state, you also have you also populate the here in this avoided crossing. And now you see that somehow the excited states like influence the population of the ground state as well. So this is the same for the second order QPT, but now the speed is larger and also the number of bosons is larger. And again, you see some population of excited states. Anyway, I have to run because I have the last 5 minutes, and I hope to manage it. So I'm at the last point. These are those analogues of ESQPTs in other systems. So I know 3 such analogous systems in which you can observe close analogues of ESQPTs. The first is the periodic lattice systems, the second is periodically driven system, and the third is the systems with continuum spectrum, that means in our case the tunneling systems. So I will briefly explain all those. So the periodic lattice systems, so the archetypal example of such a system can be this, again, the Bose-Hubbard model, but taken in the full n-side form. That means you have like a lattice of sides. It can be like 1-dimensional or 2-dimensional. The dimension is d. So you have like n lattice, like n sides in this dimension d, and you have like interactions between the bosons. You have hopping terms, etc. So you have the full Buddhist Bose-Hubbard model. So if you treat this problem in terms of a Hamiltonian, this would be a system with like diverging number of degrees of freedom, because if n goes to infinity, that is the size of the system, you would go with f also to infinity. But in these periodic lattices, you can usually find the dispersion relation. Instead of the Hamiltonian, you can find the dispersion relation, which is instead of Hamiltonian as a function of coordinates and momenta, you can find the dispersion relation as a function of quasi-momenta. And this dispersion relation, this EP function, gives you all the information that the classical Hamiltonian gave us for those systems we studied before. So you can, for example, calculate the level density by integration of this dispersion relation in the quasi-momentum space. So by these methods, if you've managed to find the dispersion relation, you can really find singularities in the spectrum which are connected with extremes or saddles of this dispersion relation. And actually these singularities are known. The difference from our previous case is now that the dimension of the space in which you integrate it can be even. That means if it is even, it is similar to the phase space, because the phase space always has an even dimension. So we have actually the singularities of the type we talked before, but you can also have an odd dimension. I mean, that can be, and in that case you have other types of singularities which are plotted here. But again, for degenerate stationary points, everything can be classified in terms of the index of the stationary point and the dimension of the space where you are. Here is, actually, I will not comment on this much. it is a spectrum of a one dimension, that means D1 Bose-Hubbard model. Actually, the realistic spectrum is here, and you clearly see that there are some singularities of all these here given types in the level density, or it can be also in the derivatives of the level density, etc. So somehow you can observe such effects in this type of collective systems. Well, now periodically driven systems. So this is sort of similar to these periodic, spatially periodic systems, but instead of the Bloch theory, like in the spatially periodic systems, you must use the Floquet theory. That is the theory for time periodic systems. So the setup is usually that you have a Hamiltonian H0 and again lambda times H prime, but now this lambda is a periodically changed function. It can be either like a monochromatically changed function, so sine or cosine, it does not matter, or it can be like a chain of delta function. That means you have a kicked system. So these are two basic types of driving which you can have. And it turns out that this periodic driving produces in the system or brings into the system a qualitative change. So it produces a completely different dynamics of the system. So there is this Floquet theory. You can actually introduce a stationary Hamiltonian HF, which describes the dynamics over one period of this perturbation, and somehow this Floquet Hamiltonian can have a completely different energy landscape than the original Hamiltonian. Here is an example. You start with this H0, so the energy landscape of this H0 can be, for example, something like that. So the system is totally unstable, sits on top of this, but then you can apply either the either the monochromatic driving or the delta functional driving, and you produce different energy landscapes which partially stabilize the systems at some points. You can have partial stabilization in some cases, but you also produce ESQPTs in the spectrum of this effective Floquet Hamiltonian. So such effects were described in the literature, and it is also very important because those periodically driven systems are experimentally available. They can be they are available in those quantum simulators. So again, this is a very interesting for me field where this idea can be applied, but it's sort of analog of an ESQPT in a similar but not the same system. So finally, and I did not manage it because if Kuro allows me to finish this little piece I have, and okay, because it's already 1 hour, I'm really sorry for speaking too long, but okay, I will be short here because I know that Pavel Stransky will have a talk about this. The analogues of ESQPTs can be found even in systems with continuous spectra, which seems like strange at the first sight, because how you can define the level density in such systems? I mean, the ESQPT is a singularity of the level density. So what is the level density of a system with a continuous spectrum? Indeed, it exists. Actually, it is known. It is called a continuum level density, and it is defined in a special way. I will not discuss that. An interesting point is that this continuum level density is naturally a complex function. That means it takes complex values, and it is defined also in the complex energy domain, which is connected with resonances somehow. So we have a complex level density of a complex energy, in fact. And now the maybe important thing for us is that this continuum level density, this strange quantity, which is like defined in, but actually that originates from molecular physics. It is, for example, in the tunneling case, we are considering here like one-dimensional systems with 1 degree of freedom. When you have continuous energy, that means the system makes a tunneling through this system of barriers, for example. So in this case, the continuum level density can be related to the transmission amplitude through this system of barriers. That means the tunneling amplitude, that the amplitude that the particle tunnels through the barrier. The amplitude has like the absolute value squared is of course the tunneling probability, the transmission probability, but the phase of the amplitude determines the phase of the transmitted wave somehow. So in principle, this continuum level density is a measurable quantity, okay, because it is directly related to this transmission amplitude. Now here you see the level density obtained from the numerical calculation actually for this system of barriers. And okay, you can now, that this is an important point which I don't manage to explain here, but somehow this continuum level density is connected also to the time somehow, to the time shift, which has the tunneling particle with respect to a free propagating particle, basically, okay? So there is a known relation between this complex level density and the time shift, okay? The point is that the time must be calculated in the complex domain. So we have a complex time, that means we are, on the theory side, we are approaching to this domain of instanton solutions of the tunneling problem, etc., etc. So I will not go to that. So we have like some complex generalization of the classical dynamics. We can define some complexified trajectories for which the time can run either along the real axis or along the imaginary axis. I don't want to somehow enter that. I just wanted to point out that this relation I mentioned is very similar to the relation which we have in bound systems with 1 degree of freedom, where we know that the level density is essentially the period of classical orbit divided by 2 pi h bar. Okay, so this is the period of classical orbits. Now we have a very similar relation, but this is this mysterious complex time shift. Now it is clear then that these stationary points which you see here, they of course must produce some singularities in this complex time, because okay, those are essentially the points where the particle stops. Sometimes, for example, if you are here, the particle stops, so there must be some anomalous time shift, of course, of this tunneling particle. And those stationary points of the Hamiltonian are connected to some singularities in this continuum level density. Now, the interesting point is that the singularities are different in the real and imaginary parts of the level density, which is somehow, for example, here you see that there is like this divergence, but in the other you see the step, etc. Sometimes it's inverted, etc. So this is a very interesting extension of the ESQPT classification to the dual form, where you have like separated ESQPTs in the real and separated ESQPTs in the imaginary part of the level density. And this is where I wanted to end. I'm sorry for taking too long, and I hope that somehow we all feel happier now, like those people in the movie. At least I feel happier because I'm already finished, and I can take beer or something now. But before, you probably ask some questions.
Okay, thank you very much, Pavel. Thank you. Thank you. It's a long talk, and but I think it's been very, very interesting, and you've been truly a flow. You have flown over the ESQPT field, and you have given a very nice picture of the different things that can be done, and some of them too brief, but as you mentioned, many of them will be treated in the different talks in the series. But I think this is the best way of starting the series, opening our appetite for more. So now it's time for questions. So any of you that have any question, you can. Yeah, I don't know. You can raise your hand now in Zoom because I cannot do it, but maybe it's because I'm a host. So you can either raise your hand and then or just unmute and ask Pavel whatever you find whatever you want to ask.
Puro, can
maybe
I make a comment?
Yes, Franco, of course, you can make a comment. You as many comments as you want.
Hello, Franco.
Hello, Franco.
I'm sorry I missed the first few minutes of your talk because I had difficulties connecting, but I listened most of it. So thank you, Pavel, for the nice review of all the material. So a few comments. I mean, you covered many things, so there are many comments that I would like to make. But let me just say only a few. First of all, on the part 2 of your talk about the different models, I would like to classify those models, algebraic models, in terms of the group or the algebra that describes them. So there are those described by a single algebra, like U6 or U4 or U2. Then there are those described by the coupling of two bosonic algebras, like U2 cross U2, U3 cross U3, and so on. So the Dickey model that you presented is one of these examples of, can be written in terms of U2 cross U2, because if you add an additional boson to the B, then you have two SU2 algebras. So in the usual form, instead of having SU2 cross SU2, you have the Heisenberg algebra H2 times SU2. So there are all these classifications. And so here I would like to say that still what we will need to do in this area is that of paying a little bit more attention also to products of fermionic algebras times bosonic algebras. This is an area which we started years ago, but which needs to be further explored. You already have indicated many cases, but it would be interesting to explore that further. And then the other comment that I would like to make is to section 5 of your talk, the tunneling, so-called tunneling systems. Yes, these are very interesting systems because physically can be realized in the laboratory. And this is the situation in which, as you show there, the potential has many different minima. And this is an area which is of great interest to experimentalists right now. There are two applications of this. One is to molecules, where you have different states, different configurations appearing, like in acetylene, there is the case of the linear configurations, and then there are other configurations with bent structure. And also in the case of nuclei, there are the so-called configuration mixing states, which have been recently analyzed by Ami and Noam Gavrielov. So this is an area which I believe is going to be very important to develop further. So I was very glad to see that you put that area on, because it's one of the areas which needs further exploitation in a way, to try to actually see whether in physical systems the level density, which is actually measured, will be well described by this by these models, these algebraic models. So I think that a lot of still remains to be done in this area, and I'm looking forward to more and more applications of these methods to physical systems.
Hey.
Thank you, Franco.
Pavel, can I ask you something, Pavel?
Yes, sure. I mean,
okay, first of all, I'm happy to see you, in fact, all of you. It's been a long year. And also thank Kuro and Jose for organizing this session. It's really great. But coming to your lecture, can you go back to this view graph of 205, the different modules? When you say which systems, no, that one. One
This
more,
one.
no, another one. The one when you write the different algebras with Boson.
Oh, you mean this?
One. I just wanted to ask you about the last one. The last one, first of all, you're denoting it by K, not by J. Is that SU2 or SU1?
No, it is deformed SU2. It is a deformed SU2. We had we had a paper some years ago also with Jose Enrique and Pedro and others describing this type of system in terms of SU11, which can also, but you can also do it. It was actually published in this paper, which is indicated here, Eva Maria Grafe. It can be done also in terms of a deformed SU2.
Okay. And the second question, you correctly say that you cannot get all the information about ESQPT from the classical limit. Now, in my language, when we're considering the classical limit, this is like the energy surface, the expectation value in the coherent state. This is the classical limit. But it's always puzzling me. One can construct excited surface, by using not the condensate that we're used to, but some kind of like excited intrinsic state, and calculate excited surfaces that will have, like in the vibron, many quantas, not just the condensate. Now, would that?
I think this idea of those excited surfaces, they are very closely connected with the adiabatic separation of some dynamical variables. If this dynamical adiabatic separation exists, then probably this concept makes sense and can be applied. But in the general case, for example, we also showed that this especially happens if you have like 2 degrees of freedom, for example, which very much differ in their speed. So there is one fast degree of freedom and the other is slow. So in this case, you certainly can draw the excited surfaces with respect to the, in this case of the separation, this idea can be applied. But if there is no such separation in this language, if you have a 2-dimensional system where both degrees of freedom are similarly fast, then probably I think you cannot construct such surfaces. So you must use the full dynamics.
Okay, thank you.
I would like to ask a question and a comment. First, the comment, thank you, Pavel. It was really, really nice review, many subjects. My question is about the quenches. So usually the quenches are done in this way you mentioned, which is I started one parameter in the Hamiltonian and then suddenly changed the parameter and evolved. But this is just, in my view, it is just one way to build any initial stage which is not a stationary state. So my question is more general. Do you think there is some particular advantage in doing this kind of thing? Because, for example, in this example, it is very, very nice when you are not over the unstable point or you are far or close to this unstable point. You could just put, for example, a coherent state there or any Gaussian state as an initial thing. Yeah, you will see very, very similar things. So my question is there any advantage in doing this way, or is it just one possible trick to select the initial state?
No, I think certainly, you can do it in as you say, if I understand properly, you do not need to start from an eigenstate of H0 or something like that. You can put, like, place a state into some Hamiltonian, and that state will somehow evolve, and it can reflect, in our case, it can reflect the stationary points. That means the ESQPT singularity. So certainly it can be done. I'm just talking about that in this language because somehow, I mean, it's traditional that people usually think about the quench in this way. And also you can very easily predict in this way whether your final state, or the initial state expanded in the final eigenbasis, whether it will overlap or not with the ESQPT region. So it's very easy to determine if you present the subject in the way I did, but there is no limitation to this way of quenching, certainly. If I answered your question, I'm not good.
So are there any other questions or comments for Pavel?
Another comment, perhaps, if I can say, is that one area which looked very interesting was that you mentioned on the part 5 of periodic lattice systems.
Yes.
This is an area which, in my opinion, also will need some additional work. And I tell you because when we published this article in Crystals, it was put on the cover page of the journal. And I continuously get notes from them saying, could you please study some other system of this lattice? And I think it would be interesting to pursue that. There was also a lot of work that Michal Maciek did while he was here, which was not published, and it would be very interesting to try to develop further that work. So this is another really interesting area where we can contribute a lot.
Yeah, I actually, you in this that is in this second paper, you managed to really calculate the dispersion relations for graphene-like systems, which is like very interesting thing by the algebraic means. And
yes,
certainly this is a very interesting area, yes.
Mm-hmm. So there is a question in the chat, Pavel, from Jonathan. I have heard that quantum phase transitions are forbidden to happen in 1D and 2D systems at finite temperature. For example, the Mermin-Wagner theorem. Are the ESQPT counterexamples of this theorem? Please, could you comment?
I'm not sure whether I'm the right one to comment. I don't think. I think it's actually something different, because here probably the dimension is the spatial dimension. No, like if you have like one-dimensional Ising model, there is no thermal phase transition in this 1D Ising chain, but it is a system of different kind in the sense that I mean, in this case, okay, first of all, we are not studying the thermal phase transitions, but second of all, this 1D Ising chain is not a fully connected system. I mean, it's a locally interacting system. So I guess all these theorems of this type probably do not apply to the systems where which we showed, because if we speak about the dimension, we already speak about the number of degrees of freedom mostly, not the spatial dimension of the system. So okay, it's not maybe clear what I said, but I think that those, I mean, the ESQPTs are not counterexamples of these theorems, certainly, but they somehow go beyond those theorems.
And Pavel, I have a question in the next slide or the following. When you speak about the continuum, I know that Pavel Stransky will speak, but then in such systems you can also have bound states, and you can mix the bound and continuum states.
Yes. We have even, I mean, we have now like this is now submitted, and it's again an archive. It's like a very recent submission, where we had a short communication about this, and this is like a more detailed version with more examples. And we also have an example there with bound states. But so indeed, I mean, but okay, we do not have an example where you would have an ESQPT in both bound and free dynamics. So, but in principle, it can be done. Why not? You would have like a potential which would have some, bound states and an ESQPT in the bound region as well. So you can play with that in this way. Actually, it can also be certainly generalized to higher dimensions, because the straightforward way is to generalize this to separable systems, like, for example, to spherical systems, which are used in molecular physics or in nuclear physics. So you have a spherical potential, so everything can be repeated somehow. This 1D theory can be transformed there. And I think also that these things are interesting because in molecular physics, there are like old papers which detected some singularities connected with these stationary points of the tunneling potentials, but they always treated them in a special way. I mean, they had a special potential, and they calculated somehow the singularity, tunneling singularity connected with the stationary points of the tunneling potential. But I mean, the theory is very easy actually and elegant, using this complex extension of everything. So we are pretty much satisfied with this contribution.
Thank you, Pavel.
May I ask a question?
Of course.
Yes. Everybody can ask, as far as I understand.
Well, again, I will start. Thank you for this very nice and clear talk about ESQPTs. Now, one of the systems that you mentioned as possible fields in which we can apply this excited state quantum factorizations are dissipative systems, open quantum systems. But you didn't say much in the talk about them, although you have a section in your review article.
Yeah.
So can you comment a little bit about dissipative system, perhaps their relations with exceptional points and accumulation of exceptional points in the spectrum of dissipative systems?
Okay, very briefly, so I'm not really an expert in this area. That was actually the area of Tobias Brandes, who cannot attend already. But okay, in general, the dissipation destroys the signatures of ESQPT somehow, because the signatures are still present on some level, but once the dissipation becomes too strong, that's gone. I mean, all the effects are disappear. And actually, what was studied in these systems was some special kind of feedback control, which could restore the signatures of the ESQPT, which was for me like a very interesting subject, like the control parameter of, for example, of the Hamiltonian, which is subject of dissipation also. I mean, the system described by that Hamiltonian is subject to dissipation somehow. But now the parameter of the Hamiltonian of that system is changed with respect to some dynamical observable, which is like at the intermediate value of that dynamical observable at that moment. So it makes some change of the control parameter. So this is like a feedback controlled system. I did not mention that type of driving in my talk because it is already relatively exotic somehow. And this feedback control is able to restore the signatures of the ESQPTs even in the dissipative system. That this is what I would say. But I'm not. I have to say I'm not aware of some links to the exceptional points or to these concepts in connection with the dissipative systems. I think this is a completely open area. I think probably there can be like very interesting studies probably can be performed in that area, but not much has been done.
There are examples of closed systems without ESQPTs, but when you put them in contact with an environment, so you put a dissipation, then of course the spectrum, when you open the system, goes to the complex plane.
Yes.
And then when you put the system in contact with an environment, there appear divergences in the density of states in the complex plane because of the dissipation. So this is the inverse of the example that you discussed before. No?
No, it is similar actually to those periodically driven systems when you can somehow an effective Hamiltonian, which is produced by some effect like periodic driving or dissipation, has some critical effects which were not present in the original Hamiltonian. But I would just warn that in this case of dissipation, well, I never worked actively in this field. So, but I just wanted to say that this effective Hamiltonian in this dissipative case, which is complex value, non-Hermitian, of course, it is not as far as I know, it is not the full answer. It is just like it's a part of the dynamical equation only, and the part with the dissipators is not fully included in this Hamiltonian. So this is not. I mean,
this is an interesting point because you can include part of the dissipation into an effective non-Hermitian Hamiltonian, but then you are left with a piece that is pure quantum.
Yes,
and it would be interesting to investigate the relationship and between these two pieces and if there is an Esqpt, if it is related to the classical part or to the quantum part, or how you can manipulate both terms. Yes.
That would be interesting. Yes. Okay, that's for me. It's also a nice field. Yes. Somehow I see as a promising field this periodically driven systems, because there are really like piles of literature on these like on the experimental realizations of such drivings, on production of some new phases by this periodic driving. So this is a very exciting field, I think. So similar can be said probably about this dissipation, although there might be slightly more difficult to produce like a controlled dissipative system, but I don't know. I'm not an expert.
Okay, thank you.
Not at all.
So, okay, let me, well, if there are no more questions, no comments, I would like to thank very much, really, Pavel, for the nice talk, and it's a 1 hour speaking, which is a good exercise, and
which is too much.
Too much, yeah. I now and online speaking, which is we all have now experience with online teaching and online meetings, and it is very strenuous, quite tiring, and so I am really grateful that he apart from doing the effort, also he manages to do such a nice and beautiful introduction to the subject. So I will then I would like to say hi to everybody, and I hope that you all stay well and safe. And we will keep in touch through the mail list, and we will announce the following seminars. As you know, next week it will be Sergio Lerma who will be speaking basically from about autocs, or these out of time order correlators and the relationship with excited state quantum phase transitions. Okay, so thank you to everybody, and stay safe.
Corol, Jose, thank you very much for this initiative.
You're welcome.
Yes,
You're very welcome. It's a
I
pleasure.
really also wanted to emphasize this, that this is really, again, this is a great idea, and thank you very much for this effort, and this is a great thing.
It will be even greater once we meet again in person. Yeah. But this is the substitute. Okay.
No, at least I have the feeling of a real meeting. I mean, in the sense that also Franco make a lot of questions, and me too. So it was like a real one. So it
looks like normal times are returning.
Let's hope.
Yes.
Let's hope.
Yes. Yes.
Okay. So very best regards for everybody.
Yeah.